Welcome back everyone. Study with Adu here. Your study with Adu. Our channel is back. So please like to our video, subscribe to our channel, enable the bell button, and comment your opinion, suggestions, and doubts. I'll reply for sure. Now we have completed only one chapter from the physical chemistry full revision. We have to complete how many five to six more chapters, taking time. A lot of time we are taking for one chapter. What 1 hour and on we are taking, right? So I don't know how we'll complete it. We'll take 6 hours for 6 chapters, but still I should tell everything. Solution also I have not completed it in a proper way because everything can't be told in in a 1 hour and all. But we have to make it complete, right? So from now onwards I will be just telling the most important concepts from the chapter. Most important concepts. Okay. Next chapter is electrochemistry. This chapter is very odd chapter. Very odd. Not very odd. Some people feel this chapter tough. I don't know why. But this chapter is easy. I also felt this chapter tough. But really this chapter is easy. First of all, this chapter is telling us about different types of cells. Different types of cells. First of all, this chapter is giving us the idea of galvanic cell. Galvanic cell. It is telling them what is a galvanic cell. It converts Gibbs energy of a reaction to electricity. A cell which converts Gibbs energy of a reaction to electricity is called a galvanic cell. Electricity is called a galvanic cell. The simple example is that. Look, that is example of Daniell cell. That is Zn and Cu is used in Daniell cell. So Daniell cell. So Daniell cell is we are having 2 tumblers for Daniell cell. Very untidy tumblers. One second. Okay. Why is it not giving us a proper idea? One second. I will draw it once again. Okay, I'll copy paste this thing and make it somewhat short. Copy paste. Yes. So I'm drawing a galvanic cell. Here inside we have something like this. Here also we have the same thing, something like that. Yeah. So it's connected with a wire. And there is a salt bridge. This is a salt bridge. Okay. This is Zn strip. This is copper strip. The solution is ZnSO4. That solution is CuSO4. Here what happens, you know that here what's the reaction? This is called anode and this is called cathode. Okay. And cathode is having a what charge? Positive charge. And anode is having a negative charge. Okay. Yes. This is what we want. What happens is that zinc is like in this compound. It is like what? So what's happening here is that this compound, this thing, zinc doesn't like electrons with it. So what? It's very caring mind. It becomes Zn2 plus and leaves its 2 electron. This 2 electron which it is leaving goes through this wire like this. Therefore, as electron is moving in this direction, current is moving here. So current is produced. This electron goes to this copper. This copper solution, and the electron is here near the at the end of the copper electron. And the solution is having Cu2 plus. Cu2 plus is very much need of 2 electrons. So it will see these electrons and it will pull the 2 electrons and become Cu, a solid Cu. And it will this will come here and they react together and it will be stuck into the electron. So at last what happened, after some time this Zn Zn what it's doing, it is giving its 2 electron and coming back to the solution. It gives it 2 electron and it is coming back to the Zn 2 plus solution. It is coming back. So at last what happened after some time, the zinc electrode vanishes. Like after giving all the electrons, it becomes like this something. It vanishes. And the copper electrode, now it is what copper is gaining all the copper solid from the copper sulfate solution, and copper electrode will be like, one second, copper electrode will be like become big. Copper electrode become big. This is copper electrode, this is zinc electrode. Copper electrode become big. So this is what happening in a galvanic cell. Here what is happening? Here due to this reaction there is a Gibbs energy. That energy is the cause for what? Electricity. Okay, so this is about the reaction. Why are we using the salt bridge? It is to complete the cell and to maintain electric neutrality. And I don't know, because in NCERT this thing is not written. Characteristics of salt bridge and all is not written, so I'm not telling about it much. Okay, so these things are over. This is basic working of a galvanic cell. So galvanic cell, one second, yes. So now galvanic cell, basic working we know, we drew it and we understood. Now in a galvanic cell, so I will tell you something what's happening in anode, in a Daniel cell. I'm taking example of Daniel cell. In anode what is happening? Zn solid is becoming Zn2 plus and it's giving its 2 electron. in cathode Cu2 plus 2 electron is it's becoming what? Cu solid. Okay, yes. So this is happening in the reaction. So first of all, you know that for a current to flow there should be a potential difference. So somewhere there is a potential difference. That's only the reason for flow of current. The potential difference, that look, here a negative charge is there, here a positive charge is there. So current flows from positive to negative, this direction current flowing. So you know that cathode is having a positive charge, anode is having a negative charge. So from how we will assign this electric potential? So scientists found out a way. They told that the electrodes have a potential, that is cathode have one potential and anode have one potential, and they called them the electrode potential or the reduction potential. So what they told is that we can assign a specific value of potential to each electrode. That is, if I am having electrode potential of E naught, one second. Yeah, electrode potential of Cu2 plus becoming Cu. Cu2 plus becoming Cu. How to find it out? One second. Electrode potential of Cu2 plus becoming Cu. It is positive because a cathode is positive here. It is positive. Why it is positive? You know that copper 2 plus is really very eager to become copper by gaining 2 electron. So they are telling that copper 2 plus is reduced to copper. Really copper 2 plus is very much active to reduction. It really wanted to become copper. So Cu2 plus is very much active. So it is having a positive reduction character. Positive reduction character means positively it want to get reduced. So it's very happy to get reduced. That way we are giving this positive charge, happiness, and the value something x. Now E of Zn 2 plus to Zn, that is zinc 2 plus becoming zinc. The thing here is that really in our reaction, zinc becomes zinc 2 plus, but when we are writing electrode potential, we should write it in the reduction potential manner. Here you thought that we should write it like this, but thing is that this is oxidation reaction, but Standard electrode potential is taken as reduction potential. So we'll write it like this. So really what happened here? The reaction happened in the electrode was the opposite way. So opposite way means really we wanted in the opposite way, we put a minus. Then we give the value. Minus y. So now the electrode potential of the cell. What is the electrode potential of the cell? What is it? It is E of the cathode minus E of the anode. So here which one is the cathode? Yeah, Cu2 plus, that is plus X minus y. So that will become X plus Y. For a Daniell cell, this X plus Y's value is 1.1 volt. So we add it like that and find it out. So now we understood that what is electrode potential. Electrode potential means it is reduction potential, usually reduction potential, everything. Now how to measure? I told you that this is X, this is Y. How did they find out this is X and this is Y? That is measurement of this electrode potential. Electrode potential. How to do it? One second. How to do it? First of all, take a she means a girl. No, standard hydrogen electrode, and keep the standard hydrogen electrode. So I am telling you standard hydrogen electrode. What is the standard hydrogen electrode? It is a special electrode that is made like this. The structure of standard hydrogen electrode is take a tumbler and there is something like this. Okay, and there is gas pumps, finely divided iron, lead, platinum, a structure of like this, and we are having a position to pump H2 gas. You pump H2 gas and the bubbles will be formed in this water, and the electrode potential of this thing is called as standard hydrogen electrode, and its potential we take it as 0 volt. That is, it's like a reference. Acceleration due to gravity. From Earth's surface, we are taking a reference and we are calculating. For physics, every question, work, there is a point of reference. So this is a point of reference, and for standard hydrogen electrode, we assume that the potential is 0. And keeping the standard hydrogen electrode, look, we are taking a cell. Keep the standard hydrogen electron She as the anode, and keep whatever we needed, copper as the cathode, and use a copper sulfate solution. Now we calculate the potential of copper electrode. Here it is 0 volt. So current is really flowing from, this is some positive value, so it's flowing from here to here. So they calculate accordingly with the potentiometer, etc., the value for this cell, and we get it to be accordingly. What's the value? 1 second. Yeah, we get the value to be 0.34. We get the value to be 0.34. Okay, yes, we get the value. So like this we calculate the electrode potential for all the hydrogen electrode. And now I want to tell you how to represent a cell. Present a cell. We'll take the Daniell cell itself. You know the reaction was Zn plus Cu2 plus gives Cu plus Zn2 plus. This is the reaction. First of all, we will write the anode reaction. How to write the anode reaction? Yes, we write it like this. Zn becomes Zn 2 plus. Okay, bar to show the next electrode, then Cu 2 plus becomes Cu. This is how we represent a cell. If we are taking another reaction, that is Al 3 plus 3 electrons is becoming Al, and which one will take? And we'll take it 2 times. No need. Okay. And Na plus this is never happenable. Never happenable. Sodium and all is never happenable. 1 second. We'll take it out. Okay. We'll do one thing. We'll take this example. No, we will. This example is enough. I'm not finding a proper example. I can give a false equation. Sorry. So we will represent the cell like this. We will represent the cell like this. Now I told you what is standard electrode potential of a cell. For a cell, the standard electrode potential is the standard electrode potential of cathode minus anode. This is important. Please by heart it. Now we have Nernst equation. Nernst equation was a scientist. So we know that E naught of a cell we know, all other matters we know. Ernst wanted to find something. He was like he wanted to find the electrode potential at specific concentrations. So he found out the equation that E naught of the given cell. So E of a given cell, electrode potential of a given cell at a specific condition or at a specific temperature or at a specific concentration can be found out as E of the cell. This is the thing that we want to find, is equal to E naught of the cell, that is standard electrode potential of the cell, minus RT by NF log M by Mn plus. This was the equation he got. Normally for us, if we need to write this equation, we just write it like this. I'm not going to derive this and tell many things about this and all. I will just tell you something. Zn plus Cu2 plus gives Cu plus Zn2 plus. Cu plus Zn2 plus. For this reaction, how to write the Nernst equation? At a specific temperature, E of cell is equal to E naught of the cell minus RT by NF log. Write the equilibrium constant. So you know that this zinc is a solid, copper is a solid. The equilibrium concentration of zinc and copper is 1. In equilibrium we learned it. So just product, that is Zn2 plus by reactant, that is Cu2 plus. So this will be the Nernst equation. You substitute the E naught cell, you get 1.1. Okay, and etc. You do it accordingly. So generally we can write that E of a cell equal to E naught of that cell plus minus RT by NF. N is the number of electrons, that is for a Zn2 plus and all just 2. Number of N can be written as number of electrons involved. Okay. F is Faraday's constant, that is 96500 Coulomb. Faraday's constant. Okay. Yes. R and T accordingly you know it. R is what? Rate constant. R is not rate constant. R is what? Gas constant. T is temperature. And here you write it log QC, that is reaction quotient, that is what? Concentration of product by concentration of reactant. You learned it equilibrium chapter. This is the thing. Okay. Yes. And now by heart the value for RT by F. It is 0.059 for T equal to 273 Kelvin at room temperature. No, not 273 Kelvin. T equal to 300 Kelvin. to about what, one second, at a T equal to about what Kelvin, it's written here somewhere. About 300, that is 298 Kelvin, you can use this value. Usually you will use this value only. So you can get 0.059 by n into log QC. The reaction, the thing changes like this. Now some other important equation is that E naught of a cell, E naught, that is what, standard potential of a cell can be related to the equilibrium constant of the cell as 2.303 RT by NF, 2.303 RT by, sorry, this is the value of 2.303 RT by NF. Here it is log, here it is really ln. Okay, sorry, lnc. When we turn to log, we have to multiply with 2.303, so we multiply with that and make it log. 2.303 RT by F is 0.059 by N log QC. Okay. Now E naught of the cell is 2.303 RT by NF log KC. Okay. Underline. Very important. Now Gibbs energy and what, E naught cell. Gibbs energy equal to minus NF E naught cell. This is all just by heart it. Use it in the problem. Just by heart and use it in the problem. Minus NF E naught cell. N is the same number of electron, and delta G can also be written as minus RT ln K. Ln K means what? Equilibrium constant. Don't forget. These two equations are important. This two equation. This is also important. This is also important. These are important. Okay. Yes. Now next, by this we come to the end of the first part of equilibrium. Now we are going to start with second part, that is conductance of electrolytic cell, of electrolytic solution. You know that electrolytic solutions conduct. So there's a lot many things written here. The thing is that you just understand one fact, that R equal to rho L by A. This you learn, R equal to rho L by A. And from this, okay, R equal to rho L by A. You know. Or you can also write it as R equal to L by kappa A, where kappa is what? Conductance, or specific conductance, or conductivity. Okay. Yes. Now we use a special device to measure the conductivity of ionic solution. That device is called as conductivity cell. The structure and all is given in the book. Just look at it. Just look at the structure. So using this conductivity cell, look, it is having a conductivity cell. We can find the resistance, that is rho L by A. There is a specific length for the conductivity column, say area for the conductivity plate, and rho. From this we have to find what? Resistance. Okay. You know that for a conductivity cell, L by A is a constant, because length don't change, area of the plate also don't change. So this L by A is called as the cell constant. It's called as the cell constant. And therefore cell constant is equal to L by A. Or we can write it as R kappa. You rearrange, you will get it. R kappa. R kappa means resistance into conductivity. Okay. Yes. Now from here, now from where we will get this resistance? If we need to find the conductivity, we need this resistance, right? From where do we get this resistance? Yeah, take the conductivity cell and place it in a Wheatstone bridge. Wheatstone bridge, you know, in physics you have learned. If you don't know Wheatstone bridge, you don't have the this in learning in this EAT batch or JEE batch or board exam batch itself. Should go to 10th standard and once again write the exam and come back. So we are having a resistance, and here we are keeping the conductivity cell. Here we are giving conductivity cell because we can't keep a what ionic solution there, so we put the ionic solution conductivity cell and keep it there. And we are having the 4 resistances and galvanometer here. No current flows to galvanometer, so we will get the answer as, you know that if the value of R is R, here it is PQR. You know that R by P is equal to Q by R, you know, Q by S, therefore R equal to PQ by S, right? With this you can find the resistance. You know that G star, that is L by A, is equal to G star. This can be found out using what? Calculate the length of the column and area of the plate of the conductivity cell, you get it. So from here kappa, you know that kappa into R is equal to G. So from here kappa can be calculated as G star by R. So we get conductivity. But usually in chemistry we like all something related with molar, like we like molar specific heat capacity, molar specific heat molar specific heat, molar that, molar mass, molar this. So here also we don't need normal conductivity, we need molar conductivity. It's very simple. How to find molar conductivity? Molar conductivity, we write it like this as just divide the gotten conductivity by the concentration, okay. This is the equation. So for molar conductivity, if you want to find it out in Siemens centimeter square mole inverse, the equation is just multiply it with 1000, that is 1000 by C. This is the equation. If you want to find it out in the SI unit, that is SI unit is Siemens meter square mole inverse, then just write kappa by C itself. Kappa by C. But when we are using this equation, the C is C is measured in mole per liter, and this in kappa in Siemens centimeter inverse, okay. But when we are measuring in this, C should be measured in mole per meter cube, not liter, and this is measured in centimeter meter square, not centimeter meter square, sorry. Centimeter minus 1, Siemens centimeter inverse, Siemens meter inverse. So these two equations you by heart, and learn this thing also. 1 Siemens centimeter square per mole is equal to 10 raised to minus 4 Siemens meter square per mole. This is an important conversion. Just learn it. Now by this we come to an end of the basics of conductivity and molar conductivity, okay. Conductivity and molar conductivity. Now comes the main part of the lesson, that is many Kohlrausch law, that this and all. I think I'll take a small break and I will do with it, okay. Yes, the same video itself. So next part is what? Change in conductivity with concentration. Change in conductivity with concentration. What happens to conductivity when concentration is increased or decreased? I will take a small break and come. Okay, let us resume. You know, a change in conductivity with concentration. As concentration decreases, you know that conductivity decreases. This is conductivity decreases. Why? As concentration decreases, the number of the number of moles per volume decreases, number of ions per volume decreases. As number of ions per volume decreases, conductivity decreases. Okay, perfect. Now that's correct. Now variation of molar conductivity. Molar conductivity. What happens? Molar conductivity of a solution at a given concentration is conductance of the volume V of a solution containing 1 mole of an electrolyte. Okay. The problem is that molar conductivity is equal to kappa into volume. Kappa into volume. Okay. The thing is that when concentration decreases, what concentration C decreases, kappa, what happens? It decreases. But volume increases. Volume of the solvent increases to a high level. Very much. The problem is that kappa decreases, but volume increases very much compared to kappa. Due to kappa. Therefore, molar conductivity directly proportional to volume. Kappa is very small, so we can tell molar conductivity is directly proportional to volume. Okay, so as volume increases, molar conductivity also increases. So as volume increases, molar conductivity increases. When does volume increase? When volume increases, you know that concentration decreases. So we can directly tell that or indirectly tell that as concentration decreases, molar conductivity increases. That is, molar conductivity is inversely proportional to concentration. So there is the important thing told here. Molar conductivity is inversely proportional to concentration. And we'll draw a graph. Okay. Yes, we have a graph here. Okay. And I'm drawing KCl. This is KCl. One second. Not like this. Not like this too. One second. This is CH3COH and this is KCl. Look, when this is what volume? This is what concentration. This is conductivity, molar conductivity. Look, when we decrease the concentration of KCl and when the concentration becomes infinite, that is, concentration becomes 0 means at infinite dilution, KCl touches a value here. Right, this value is called the limiting molar conductivity or the molar conductivity at maximum dilution. Molar conductivity. But the thing is that KCl is a strong electrolyte, but CH3COH is a weak electrolyte. For weak electrolytes, they don't have a limiting molar conductivity, or their limiting molar conductivity is at infinity. Is at infinity. Okay, note it. Yes. So that's about it. So now we can tell about strong electrolytes. For strong electrolytes, what's the speciality in graph? Alpha m equal to alpha I naught m minus a c half. Y equal to mx plus c. M is negative, so it's having a negative slope. Okay. Yeah, this is this thing, and this is c, this limiting molar conductivity, and y equal to this thing. Understood? Okay. So a for different thing is different. Okay. Value of a is different. Okay. Value of A is different, but look, NaCl and KCl, I'm taking these compound. For them, the value of A is same. Value of A is same. Because they are 1 electrolytes, that is 1 1 1 1. There is MgCl2 and CaCl2. They are 1 2, that is dissociation 1 2. They have same type of A, but these two have different A's, but they have same A, that is 1 2 A, 1 2 type A. That's what it's told here. Now Kohlrausch's law, nothing. If we need to find the limiting molar conductivity, of CaCl2, it's very simple. Just add the limiting molar conductivity of calcium. No, we'll take small letter of this thing. One second. Yes, just add limiting molar conductivity of calcium plus 2 times, because there are 2 Cl, 2 times limiting molar conductivity of Cl minus. Now if we need to find limiting molar conductivity of NaCl, limiting molar conductivity of Na plus 1 time limiting molar conductivity of Cl minus. For any compound you can find it like that. 1 second. Limiting molar conductivity of K2SO4 can be found as, no need of K2SO4, we'll take another compound. CaCl2 can be found as limiting molar conductivity of Ca2 plus 2 times limiting molar conductivity of Cl minus. So this is called Kohlrausch's law. You can add the limiting molar conductivity of each ion, and you can find the limiting molar conductivity of the compound, or the strong electrolytes for strong electrolytes. Now for weak electrolyte, I told you that weak electrolyte, the graph is going to infinity, like an asymptote. Weak electrolyte, the limiting molar conductivity is at infinity, so we can not tell anything much. But there is an equation for weak electrolyte, that is, just to understand that dissociation constant, alpha of a compound of a weak electrolyte is molar conductivity by its limiting molar conductivity. Okay, and then what is the Ka for the electrolyte? Ka value for the electrolyte, you know that Ka value is C alpha square by 1 minus alpha. Alpha is equal to this thing by naught m, right? So Ka equal to C m square by alpha naught m whole square 1 minus alpha naught m minus alpha m by alpha naught m. So therefore we get Ka equal to C alpha m whole square by alpha naught m minus alpha m, not alpha, sorry, chi m or lambda. Yes, this is the equation for a weak electrolyte. Now application of Kohlrausch's law, it's given. You can just read through that if you need. Okay. Now we come back to, now we studied about what? Galvanic cell and conductivity. Now we are coming to a new type of cell, that is electrolytic cell. Electrolytic cell. Electrolytic cell. What is electrolytic cell? I told you, galvanic cell is a cell that converts the Gibbs energy of a spontaneous chemical reaction into electrical energy. So electrolytic cell is a special type of cell where non-spontaneous reactions, that is non-spontaneous reactions or reactions which are non-spontaneous reactions are happenable by what? By what method? Non-spontaneous reactions are happenable by electricity. As we pass electricity to a compound or an electrolyte, we get non-spontaneous reactions happen. This is about the principle of electrolytic, other known as galvanic electrolytic. Opposite of galvanic cell is what electrolytic cell is doing. Now it is like you know that Cu2 plus getting 2 electron and becoming Cu is a common reaction. Cu likes to do the same. But Cu doesn't like of becoming Cu2 plus and 2 electron. But this reaction is what really? This is non-spontaneous. But this reaction is made spontaneous. By what? Passing electricity to this copper. That's why we are telling non-spontaneous reactions are made happenable by electricity. And now we are telling there are 2 Faraday's laws. Just read through that law. Faraday's law. Faraday is telling that how much amount of current is passed through a compound, that much amount of reaction happen. That's what Faraday is telling. So that same thing can be shown by this reaction. Ag plus Ag plus 1 electron give Ags. What is the charge of 1 mole of electron? You understand, charge of 1 mole of electron is 1 Faraday. That is 96500 coulomb for charge on 1 mole of electron. So in this reaction, 1 mole of electron is added to silver and the silver is made as solid silver. So we are 1 mole of electron means 1 Faraday. Now you know that Q is equal to IT. You have learned in physics, IT. So we need to find out how much current is produced. That is Q. That is how much? 1 Faraday by T. Time is 1 minute. No, 1 second. So in 1 second, 1 ampere current is produced here. Not 1 ampere, 96500 coulomb. So 96500 ampere current should be passed through. One second. Some problem is happening here. No. Accordingly, 1 second. No need to do like this. It is very confusing. What happened to my rubber? That's the reason. Yes. So we are having Q by T. So how much current should be passed? If a question comes, divide the Q by the time for which the current is passed. Q by T. If Q is 96500 by time. That will give you how much current should be passed. Okay. Yes. That's how to do the questions. Now another example, that is Al3 plus. Now we will do a question itself. Then it's very simple. A solution of CuSO4 is electrolyzed for time equal to 10 minutes with a current I equal to 1.5 ampere. What mass of copper? So they are telling that a CuSO4 solution is taken, and CuSO4 means Cu2 plus 2 electrons gives Cu. So this reaction is happening for a time 10 minutes and what current 1.5 ampere current. You know that Q equal to IT. First of all, find this Q. Q equal to 1.5 into T is how much? How many minutes? 10 minutes. That is 60 into 10 minutes, right? So 60 into 10. 1 minute is 60 seconds. So 10 minutes is 600. So that is 15 into 6, 15 into 5, how much? 75, 90. 900 coulomb. 900 coulomb charge. So 900 coulomb charge is here. Look at the equation. Cu2 plus 2 electrons gives Cu. Here 2 mole electron is there. 2 mole electron is there. That will give us 1 mole copper. 1 mole copper. Okay. 1 mole copper. Perfect. So if you are using 1 mole electron, 2 mole electron, 1 mole copper. No need, I will write it like this. 2 mole electron, how many, what's the charge? Yeah, 2 Faraday give us 1 mole copper, right? 2 Faraday, 2 mole electron means 2 Faraday. So 1 Faraday give us 1/2 mole of electron, 1/2 mole copper. You know that here we are only having 1 Faraday means how much? 96500 coulomb give us 1/2 mole of Cu. Right, yes. So how much does 900 coulomb give? How much does 900 coulomb give? Simple. 1/2 into 96500 into 900 mole of Cu. Calculate this. You get okay, mole of Cu. They asked, the question to us is how many gram of copper is what formed. You know that how many moles are there into molar mass. How many moles are there into molar mass will give us how much gram is deposited. What's the molar mass? It is 63 gram. 63 gram. You multiply it with 63, you get the answer to be 0.2938 gram. Top 2938 gram. So the questions will come in this manner itself. This is the manner of asking question. Top. This is the manner of asking question. Okay. Now we are going to talk about products of electrolysis. So what product we get after electrolysis? Products of electrolysis. Okay. First we are talking about molten NaCl. There is only NaCl is there in the middle, not in water, not salt solution. Molten NaCl. So there is Na plus and Cl minus. You know, in electrolysis, in galvanic cell, we told that anode is negative and cathode is positive. No, cathode is negative and anode is positive. No, sorry. Anode is what? Anode is negative and cathode is positive. But in galvanic cell, in electrolytic, 1 second, something is happening here. Yes. So in Daniel cell we told that anode is negative and cathode is positive. But in electrolytic cell, really anode is positive and cathode is negative. This is the difference here. Cathode is negative. So Na plus will go to the cathode and Cl minus will go to anode. Na plus will go to the cathode. Na plus will go to cathode and accept 1 electron and become Na2 plus and become Na solid. This is reduction. So reduction takes place in cathode. That we already know. Reduction in cathode, oxidation in anode. Reduction in cathode, oxidation in anode. So reduction take. Cl minus went to anode. Cl minus went to anode and told that I don't need one extra electron, and it becomes Cl plus electron. This is called what? Oxidation. Oxidation. Okay. Yes. Right. Really 2 electrons happen, because then only we'll get Cl2 minus 2 plus, right? So oxidation happens at anode. This is the case of molten NaCl. It's case of molten NaCl. Molten NaCl. Okay. Now once again let me take NCERT and explain. Yes, we have the electrochemistry chapter here. Yes. So here is the reaction that we told now written. Here it is written. Now during the electrolysis of aqueous sodium chloride. Now we are talking about aqueous sodium, that is NaCl will be there plus H2O is in the medium. So aqueous sodium chloride. What happens? What happens in aqueous sodium chloride? One second. Yes. So there is Na plus. What is it? Aqueous sodium chloride, there is Na plus and H plus. There is a competition happening between Na plus and H plus to go to anode. So who will be first going to anode? So look at the electrode potential value. Sodium is having minus 2.71 volt and hydrogen is having 0 volt. So going to anode means they should be oxidized. Oxidation should happen. Oxidation means who have less reduction potential. Reduction potential has oxidation. Who has less reduction potential. Among them who has less reduction potential, for sure negative is less. So Na plus wins the competition and but the problem is plus charge goes to cathode, not to anode. Sorry. Plus charge compound go to cathode. The problem here is there are 2 compounds, Na plus and H plus, and there's a competition between Na plus and H plus to go to cathode. Cathode means reduction is happening. Reduction means who have more reduction potential. More potential gets reduced first. Who have more? Minus or this? Yeah, for sure hydrogen have most. Therefore hydrogen gets reduced. That is H plus 1 electron give half H2. We get the reaction. Okay. Yes. Net reaction as cathode is this thing. That's written here. H2O is split into H plus plus OH minus. The reaction is written. Net reaction is written like this. Okay. Yes. So competition at cathode is now over. Now we come to anode. At anode, there's a competition between Cl minus and what? OH minus. There's a competition between Cl minus and OH minus. So look at the electrode potential. Who have less electrode potential wins. Potential goes to anode. Among them, chlorine has less. What? OH minus, they have written it in this form. That way they have written like this. It's really OH minus. Okay. OH minus. OH minus really is having electrode potential 1.23. It's having less. For sure, OH minus should go to what? Goes to anode. But here there's a twist. Here there's a twist. Instead of OH minus, Cl minus is going to anode. The thing is that the reason for that is OH minus is a drug addict. It's a drug addict means, for fun I'm telling, OH minus is mad. What OH minus is going to do is that when it is in this reaction, OH minus is having what? Over potential. Over potential means oxygen is having over potential, and hence this is having what? Over potential. Due to over potential, this value of 1.23 will increase. Therefore the value increase, and what happens? The value go beyond 1.36 volt. Therefore chlorine gets oxidized. Therefore, due to over potential of oxygen, reaction is preferred. Therefore Cl minus get oxidized, not OH. This is the tricky question. This is a tricky question. This is a tricky question. They can ask you. Tricky. Okay. So the net reaction is written here. You can just read through it. All the reactions that we explain now is written here. The standard electrode potential are replaced by electrode potentials given by Nernst equation to take into account the concentration effects. During the electrolysis of sulfuric acid, the following processes are possible at the anode. Okay. Now we are telling about what? Electrolysis of sulfuric acid. That is H2SO4. And we will also use H2O is also there in the medium. So there are two things that can happen at what? There are two things that can happen at the reaction is cathode is simple, but reaction anode is complicated because once again OH minus is coming over potential, that potential, this potential is coming. So at anode reaction, cathode reaction we get H plus, and for sure we are going to get hydrogen, what? H2, as the same this reaction is going to happen. But at anode, will this reaction happen with electrode potential 1.23, or this reaction happen with electrode potential 1.96? Yeah, they are telling that both the reactions can happen. If the solution is dilute, then oxygen will be evolved. If the acid is concentrated, then what happened? We get H2OA2 minus. This reaction is preferred. Okay, this is very important. They can give you that when concentrated H2SO4 is electrolyzed, what is the product? It is S2OA2 minus. Product is S2OA2 minus at anode. But if it's dilute, we get oxygen at anode. Now many questions are there. You can do it your own. No time. Now we come to application of electrochemistry. How to apply electrochemistry in the daily life. So batteries. Any battery or a cell that we use as a source of electrical energy is basically a galvanic cell. Really, batteries are galvanic cell because they are like giving us electricity. Look, we don't provide electricity to battery. What we do is that we put battery into a device, electricity is generated by the battery. Therefore, it's a galvanic cell. Batteries are galvanic cells, okay, where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. So the voltage, the EMF of the cell should not vary, then it's not a good battery. So accordingly we make battery. So there are mainly two types of battery, that is first one is primary, then secondary. Primary batteries are a non-reusable battery, that we can only use it once, after use throw it away. No, we cannot recharge. That batteries are called primary batteries. One most important example is this battery, that is normal dry cell or a Leclanché cell. Okay. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused. We cannot reuse it again. The most familiar example of this type is a Leclanché cell or a dry cell. Okay, which is commonly used in transistor and cloak the cell of. Okay, what is the anode and cathode in a dry cell? That is important. The cell consists of a zinc container that also acts as anode, and the cathode is a carbon or a graphite rod. So the anode is a carbon or a graphite rod, cathode is a carbon or a graphite rod, and anode is a zinc container, and bipowdered, and between this cathode powdered MnO2 is there and carbon is there. The space between the electrodes is filled by a moist paste of ammonium chloride and zinc chloride. Okay, and the electrode reaction is given. Electrode reaction is very simple. Zns anode, what happening? Zn is becoming Zn2 plus 2 electron, same reaction as the anode of the Daniell cell. At cathode MnO2 NH4 plus 1 electron, we are getting MnOOH and NH3. MnOOH and NH3. Okay. Learn this reaction means just go through it. In the reaction at the cathode, manganese is reduced from plus 4 oxidation state to plus 3 oxidation state. That is MnO2 to MnOOH. OH is having minus here 3. So here 3 plus 3. Here 1, 2, 3, 4 plus 4. So here reduction is happening. So therefore you know that at cathode what happens? Reduction is happening. Okay. That's over. Now we come to next example of primary cell, that is mercury cell, that we use in that hearing aid, small silver color cell. That is mercury cell. Yeah, this thing, small silver color cell. This is called mercury cell. Okay. Mercury cell suitable for low current devices like hearing aid, watches, etc. Okay. What is the anode? It is a zinc mercury amalgam. ZnHg is the anode, and a paste of HgO and carbon as the cathode. Okay. So anode is zinc mercury amalgam and HgO Zn paste. HgO and carbon paste is the cathode. The electrolyte mixture is a paste of KOH and ZnO. Okay. Now anode reaction, ZnHg plus 2OH minus is giving ZnO. Here what is happening? Zn0 to Zn2 plus oxidation. Okay. Now here HgO to H2O plus 2 plus. HgO means Hg2 plus is becoming reduced to Hg. That's the cathode reaction. That is reduction. The overall reaction is given here. You can just go through it. Okay. Yes. The cell potential is 1.35 volt, and the important thing of the cell is that the EMF of the cell is always constant throughout the life of the battery. Overall reaction does not involve any ion in solution whose concentration can change during its lifetime. That this battery has a very long lifetime, and the 1.35 volt remains constant during its lifetime because there is no ions. Here there is no ions involved in the overall reaction. Here there is no ion, but for the other above reaction I think ions were there. Yeah, there were ions. Zn2 plus ions are there. Okay. Now we come to secondary cell. That they are rechargeable battery that we use in our inverter, that this one, or nickel cadmium battery. Okay. And the thing is that secondary batteries are like, first they act as a galvanic cell, and when their power is over, they act as an electrolytic cell and they get charged back. So it's very special. Their secondary batteries are having both galvanic phase and electrolytic phase. A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. Okay. That same thing is given here somewhere in the first page. 1 second. Yeah, look this thing. Yeah. Here we are having our galvanic cell. Here current is passed from the cathode to anode. This acts as what? A galvanic cell. Now if this zinc is over, now if this zinc plate, now the zinc plate is over and this plate is very thick. This plate is what? Very thick plate is there. Very thick. Now what happened? At this position, zinc is over. Zinc plate is what? Over, and copper plate is very thick. So the no more reaction is happening. So for more reaction to happen, what we can do? Give an external voltage greater than the voltage of the battery, that is more than 1.1 volt. Yeah, here if we give more than 1.1 volt, what happened? Current flows from zinc to copper. Current flows from zinc to copper. And what happened? Current flows from zinc to copper means electron will come from copper to zinc. Electron is coming. So therefore Zn2 plus will gain that electron and become Zn, and it will regain its shape, and copper will also regain its old shape. The thin sheet will be coming. The thick sheet become the thin sheet once again, and the nothing sheet, that is the destroyed sheet, the thin copper sheet becomes the old thickness. Okay, and once again now if we give a less voltage than 1.1 volt, or just we connect the battery, what happened? It will once again have the galvanic property, and after some time, once again if you recharge it, once again it will get the galvanic property. So it's like that. Like that. Okay, so where is our chapter? Where is our part here? So that's about secondary batteries. Now a famous secondary battery is a lead storage battery. The most important secondary cell is the lead storage battery, commonly used in automobile, etc. Learn this anode reaction, Pb plus SO4 2 minus give PbSO4. Learn this cathode reaction. Learn the anode and cathode. Anode is lead dioxide. Hello. Cathode is lead packed with lead dioxide, and anode is made of lead. Just learn it. 38% solution of sulfuric acid is the electrolyte. Okay, the overall reaction also just go through. We are getting PbSO4 as the product. This is the photo of that, or the picture of the secondary cell, that is lead storage battery. Now another important secondary cell is nickel cadmium battery. Here it has longer life than lead storage battery, but it's very expensive. Nickel cadmium battery. Okay, we shall not go into details of the working and all, because the overall reaction is having somewhat complexes that we have never learned. Just go through this reaction. Cd plus 2NiOH thrice gives CdO plus 2NiOH twice plus H2O. Okay, now next one is fuel cell. Galvanic cells. What are fuel cells? They are telling galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. Okay, so they are telling that here, look, H2 plus O2. So they are told lot of things about this. Just learn this thing for this. Just learn this part, that is here hydrogen and oxygen can be burned together so that we get H2O. Look, this process is used by planned to be used by many car companies to use instead of petrol. So that what happens then, hydrogen and oxygen will pump into the vehicle, and they react, and high electricity is released, and H2O is released as a byproduct, which automatically goes through the car through the silencer to the air, and we will get enough rain also and cool the earth. So that thing. Learn this cathode anode reaction. Learn this. This is important. Okay. Let us do what is oxygen plus H2O plus 4 electron give 4OH minus 2H2 plus 4OH minus give 4H2O plus 4 electron. Here 4 electrons are involved in the reaction. Overall reaction is simple. Everyone knows. Yes. Here the thing I have told is written. Now corrosion. That is what? Rusting of iron. That is oxidation. Just read through this paragraph once. We'll read now itself. Corrosion slowly coats the surface of metallic objects with oxides or other salts of metal. Okay. The rusting of iron, tarnishing of silver, development of copper, that is clave in my language, development of green coating on copper, and bronze are some of the example of corrosion. It causes enormous damage to building, bridge, ship, and or to all objects made of metals, especially that of iron. We lose crores of rupees every year on account of corrosion. Okay, in corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxide. Corrosion of iron occurs in the presence of water and air. So water and air is important for corrosion of iron. That's written here. Why we need water and oxygen? Look, reduction. Look, oxidation and reduction. It's like a redox reaction. So water and air is important. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomena. At a particular spot of an object made of iron, oxidation takes place and that spot behave as anode, and we can write the reaction as anode. 2Fs gives 2F2 plus 4 electron. Why does this happening? Look, electrode potential is negative, so oxidation happens. That's the reason why oxidation is happening. And the background water in the atmosphere is having a potential positive potential, and therefore it forms a galvanic like cell there. Okay, electrons released at the anodic spot move through the metal and go to which another spot on the metal and reduce oxygen in the presence of H+, which is believed to be available from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. Lot many things are written, no need to worry about that and all. This spot behaves as a cathode. They are telling that this is the spot where cathode is formed. Overall reaction is written here, just learn it. Now prevention of corrosion is important. It can how to prevent corrosion is one of the simplest method of preventing corrosion is to prevent the surface of the metallic object to come in contact with the atmosphere. This can be done by covering the surface with the paint or by some chemicals like by bisphenol. Another simple method is to cover the surface by metals like zinc, tin that are inerted to react to save the object. An electrochemical method is to provide sacrificial electrode. Not sacrificial, sacrificial electrode of another method like MgZn, which corrodes itself but save the object. Oh, nice. Yes, and by this chapter is over. The summary you can read. Summary is good. You can read it for fast revision. Okay. So by this we come to the end of this chapter. I am not at all well. I am taking what chapters last 24 hours itself. I took a lot many chapters, right? So everyone, please like the video, subscribe to our channel. 1 second. This is that weak electrolyte thing called Roche's law. Let me check. I did everything. Conductivity, limiting monoconductivity. This graph. Yeah. Chi. This is the portion telling about conductivity that I did. Now anything else? Yeah, this thing also we did. This thing we did. This thing we did. This also we did. Wheatstone bridge. Conductivity cell. This is the photo of the conductivity cell. Okay, this is a photo of the conductivity cell. The area of this plate is A. The length between these two plates is L. So this will never change. That way cell constant is a constant. This thing I didn't tell. The conductivity of an electrolytic solution depends on these 5 factors. We'll read the factors. The nature of the electrolyte, the size of the ions, the nature of the solvent, the concentration of electrolyte and temperature. Okay, we read it. Now electric conductance through metals is called metallic or electronic conductance due to movement. The conductance depend on the nature, the number of valence electron and the temperature. Okay. Now they have told about different materials and all. We didn't do this. We only did this formula directly. And why a right angle triangle formed? Yes, we did this formula directly. We did this formula directly and went. Okay, that's about it. Now these things, yes, Ernst equation, equilibrium constant, Ernst equation, yes, hydrogen potential. Yeah, this is the photo of the hydrogen potential. I drew it very bad, so just look at. Now oxidation, this is the equation, this is the representation of the cell. I told you, right? Yes. Now anything else? Galvanic cell. This now itself I explained. This is the Daniel cell, and yes, the chapter is over. So thank you.